At the very edge of the sun's reach, where the warmth fades into icy silence, a handful of distant frozen bodies drift through space. Their orbits are strange, tilted, clustered, bending in eerie patterns, as if something unseen is tugging them from the darkness. Astronomers noticed these anomalies. Something massive, something hidden, was exerting a silent gravitational pull. This mysterious influence hinted at a world so distant and dim that even our most powerful telescopes had failed to detect it. A planet, possibly 10 times the mass of Earth, orbiting hundreds of times farther from the Sun than Neptune. Scientists began calling it Planet 9, a world that could rewrite our understanding of the solar system. But this isn't the first time the cosmos has surprised us. The year was 1930. A young amateur astronomer named Clyde Tombaugh, peering through the telescope at Lowell Observatory in Flagstaff, Arizona, discovered a faint speck of light inching across the starry background. After weeks of painstaking observation and careful photographic comparisons, the announcement came. A new planet had been found. The world rejoiced. For the first time in nearly a century, the solar system had a new member. The newly discovered body was named Pluto, after the Roman god of the underworld, an apt name for such a remote and cold world. For generations, Pluto held a special place in the hearts of stargazers and students alike. Children learned its name as the 9th planet. It had a mythic quality, a symbol of how vast and mysterious our solar system truly was. But soon, cracks in Pluto's identity began to show. Scientists noticed that Pluto's path around the Sun wasn't quite right. Its orbit was too elongated, too tilted. It didn't behave like the other planets. And it was small, smaller than Earth's moon. It turned out Pluto was just one of many similar icy bodies in a region known as the Kuiper Belt. Pluto's status was challenged. Was it really a planet, or just one of countless frozen relics from the solar system's formation? The debate grew heated. In 2006, the International Astronomical Union made a controversial decision. Pluto was officially demoted to a dwarf planet. For many, it was the end of an era. But for astronomers, it opened the door to deeper questions. If Pluto isn't the 9th planet, could there be another? This is where Planet 9 enters the stage. The strange orbits of certain Kuiper Belt objects, like Sedna and 2012 VP-113, showed patterns that couldn't be explained by the known planets alone. Their orbits were shepherded, pointing in the same direction, as if something large was hurting them from afar. In 2016, astronomers Konstantin Batygin and Mike Brown proposed a bold hypothesis. Based on mathematical modeling and orbital dynamics, they suggested that a giant unseen planet, Planet 9, could be lurking far beyond Neptune, shaping the outer edges of our solar system with its gravity. They weren't claiming they had seen it, but the evidence in the orbits was compelling. It was like watching the leaves rustle and knowing the wind is there, even if you can't see it. The idea reignited public fascination. Could we be on the brink of discovering a new planet? Could Planet 9 be real? Unlike Pluto, Planet 9 wouldn't be a small, icy rock. It would be massive, possibly Neptune-sized. And its orbit might take thousands of years to complete a single trip around the Sun. Finding such a world would be like spotting a single grain of sand on an endless beach. But astronomers are searching. Telescopes across the globe and in space are scanning the farthest regions of the sky. Algorithms comb through data, looking for subtle wobbles or faint flickers of light. If Planet 9 is out there, we may soon see it. Its discovery would reshape everything, not just our textbooks, but our understanding of how planets form and migrate. Why do some worlds get flung into the outer darkness while others stay close to their star? What secrets could such a distant world hold? And perhaps most importantly, what else might be hiding in the cosmic shadows? As astronomers peered deeper into the Kuiper Belt, the icy frontier beyond Neptune, they discovered that Pluto was not alone. Far from being a unique outpost, Pluto was just one of many small, frozen worlds orbiting the Sun in that distant region. And therein lay the problem. Despite its fame, Pluto didn't meet the new, stricter definition of a planet. In 2006, the International Astronomical Union, IAU, convened in Prague and made a decision that would ignite controversy for years to come. According to their updated criteria, a planet must meet three conditions. It must orbit the Sun. It must be massive enough for gravity to shape it into a near-spherical form. It must have cleared its neighborhood of other objects. Pluto checked the first two boxes, but the third? That's where it fell short. Pluto shares its orbital zone with countless other icy bodies. It hasn't cleared its neighborhood. It's not the dominant force in its orbit. That role belongs to Neptune, which often gravitationally influences Pluto's movements. And just like that, the beloved ninth planet was stripped of its title. In its place, Pluto received a new designation, dwarf planet. It joined others like Ceres, in the asteroid belt, and Eris, another icy body in the Kuiper belt that actually outweighed Pluto. These celestial bodies were still scientifically significant, but they now belong to a separate, less prestigious category. The vote that sealed Pluto's fate wasn't as monumental as it seemed. Only 424 astronomers were present for the final decision, an astonishingly small number considering the global implications. Many in the astronomical community were absent. Critics argued that the resolution was rushed, poorly communicated, and lacked consensus. The backlash was swift and passionate. In scientific circles, the decision brought clarity. It provided a consistent framework for classifying new objects being discovered in the Kuiper belt and beyond. With the floodgates of discovery opening, astronomers needed rules, and the new definition gave them just that. But for the public, it was a shock. Generations had grown up with 9 planets. School posters, textbooks, even children's songs featured Pluto as the tiny but proud member of our planetary family. To suddenly hear that it wasn't a planet anymore felt almost like a betrayal. Protests erupted, petitions circulated. Cultural icons, late-night comedians, and even some scientists called for Pluto's reinstatement. The emotional attachment ran deep. Even today, nearly 2 decades later, the debate continues. Some astronomers argue that the third criterion, clearing the neighborhood, is flawed. After all, even Earth shares its orbit with asteroids. Jupiter, the largest planet in the solar system, hasn't completely cleared its zone either. So why should Pluto be singled out? Others believe the term dwarf planet is misleading. After all, a dwarf star is still a star. Shouldn't a dwarf planet still be a planet? These arguments have led to ongoing discussions in the scientific community. Several prominent researchers have called for a new, more inclusive definition of what constitutes a planet, one that would bring Pluto back into the planetary fold. Yet the IAU's definition stands, at least for now. What this controversy reveals is something deeper than classification. It shows how science is constantly evolving. As we gather more data and refine our tools, our understanding changes. And sometimes that means rewriting the cosmic rules we once held dear. It also highlights how deeply space and science are embedded in our culture. Pluto isn't just a celestial body. It's a symbol of curiosity, exploration, and the emotional connection humanity has with the stars. But here's where it gets even more fascinating. As we debated Pluto's status, scientists uncovered more clues suggesting there might be something even larger, even more mysterious, lurking beyond the Kuiper belt. Something massive that could explain the odd orbits of distant objects. Something that fit the mold of a true planet. Planet 9. While Pluto's status was being downgraded, Planet 9's legend was just beginning to grow. And as we continue our search, The very same debates that shaped Pluto's fate now influence how we define this possible new world. Is Planet 9 a planet by the IAU standards? Will it too be challenged if discovered? Or will it finally bring consensus, and perhaps redemption, for Pluto? The story of Pluto is more than just science. It's about change, resistance, and the human desire to classify the universe. But the universe doesn't always fit in our boxes. It's vast, wild, and full of surprises. And just when we think we understand it, it reminds us how much we still don't know. Even after Pluto's demotion, astronomers didn't stop exploring the icy edges of our solar system. They pushed forward, deploying powerful telescopes, sweeping the dark skies in search of answers. And what they found was strange, uncannily strange. They discovered a handful of distant objects known as ETNOs, extreme trans-Neptunian objects. These bodies, orbiting far beyond Neptune, shared a curious characteristic. Their orbits were not random. First, they clustered around similar perihelia, the points where their paths brought them closest to the Sun. That alone was unusual. But then, scientists noticed something even more striking. These ETNOs also tilted in similar directions, forming a second layer of alignment. That double clustering, both in distance and direction, was not something you'd expect from random behavior in a chaotic outer solar system. In theory, the giant planets, especially Neptune, should have disrupted these alignments over millions of years. Gravitational nudges, collisions, or simple orbital chaos should have scattered them like leaves in a storm. But the alignment persisted. It held strong. Some researchers were skeptical. Maybe it was just coincidence, they argued. Or perhaps a statistical fluke. After all, only a couple dozen ETNOs had been found. Small sample sizes can be deceptive. But simulations told a different story. Teams of astrophysicists ran thousands of orbital models. And over again, the results were the same. The chance of these objects being aligned purely by accident was extremely low. Less than 1 in 10,000, and something had to be guiding them. Something massive. Something unseen. The data spoke for itself. These ETNOs weren't just scattered randomly through the darkness. They were being shepherded, subtly, steadily, by the gravitational hand of a much larger object. One that had eluded direct detection, but whose presence echoed in the orbits of everything it touched. That's when the hypothesis of Planet 9 became more than just speculation. It became a serious scientific proposal backed by models, math, and mounting indirect evidence. The idea electrified the astronomy community. A ninth planet, lurking in the shadows? It sounded like science fiction, but it was grounded in hard science. And it wasn't just about Planet 9's existence, it was about what it meant. If real, Planet 9 would be a true giant. Not a tiny dwarf like Pluto, but a planet with 5 to 10 times the mass of Earth. It might be similar in size to Neptune, orbiting the Sun once every 10,000 to 20,000 years. And because it's so far away, it would be incredibly faint, perhaps 600 to 1,000 times dimmer than Pluto. It would take the sharpest, most sensitive telescopes in the world to spot it. But scientists weren't discouraged. They began crafting search strategies. They calculated where in the sky Planet 9 might be hiding. They mapped its possible orbit like detectives chasing an invisible criminal. Only instead of footprints, they followed gravitational fingerprints left on distant worlds. And still, the data kept pointing to the same conclusion. The orbits of ETNOs don't make sense without Planet 9. The deeper researchers looked, the more clues they found. Some of the ETNOs even appeared to be anti-aligned. Their orbits mirrored each other in symmetrical patterns that would be stable only if a massive object were tugging them from afar. This wasn't just a hunch anymore, it was an unfolding mystery, one grounded in physics, mathematics, and cold cosmic logic. But the question remained, if Planet 9 is so big, Why haven't we seen it? The answer lies in the vastness of space. Planet 9, if it exists, would be moving incredibly slowly, perhaps just a few arcseconds per year. It would be so faint it could easily blend in with the countless background stars. And depending on where it is in its orbit, it might currently lie in a region of the sky that's been poorly surveyed, or is exceptionally dense with stars, like the galactic plane. To find Planet 9, we need patience, precision, and persistence. And yet, each year brings new advances, new telescopes, smarter algorithms, deeper surveys. Planet 9 may be hiding, but it can't hide forever. Some even speculate that when it is finally discovered, it may not be a planet at all, but something stranger. Could it be a captured rogue planet? A primordial black hole? Or perhaps an object from outside our solar system entirely? For now, the mystery remains. But one thing is clear: the outer solar system isn't as empty as we once thought, and something big, is shaping it in ways we're only beginning to understand. So if Planet 9 is real, where is it? And how does it move? That's the puzzle scientists are racing to solve. Based on gravitational modeling and orbital simulations, Planet 9 can't follow a simple, circular orbit like the planets we know. Such an orbit would bring it too close to the inner solar system, close enough that we would have seen it by now. To remain undetected and yet exert gravitational influence on ethnos, Planet 9 would need an extremely elongated orbit, an eccentric path that keeps it far away from the Sun for most of its journey. Current models suggest that its perihelion, the point where it comes closest to the Sun, could be between 200 to 300 AU. That's 5 to 7 times farther than Neptune. Its aphelion, the farthest point, could extend as far as 800 to 1,200 AU, an almost unimaginable distance. To put that in perspective, light from the Sun takes just over 8 minutes to reach Earth. It would take light more than a week to reach Planet 9 at its furthest point. Its orbital period, a single year on Planet 9, could last between 10,000 to 20,000 Earth years. Think about that. Entire civilizations could rise and fall on Earth while Planet 9 completes just one trip around the Sun. But distance isn't the only factor. The inclination of its orbit is another key clue. Unlike most planets that orbit in a relatively flat disk, the ecliptic plane, simulations suggest Planet 9's orbit is tilted, 15 to 25 degrees off the ecliptic. This tilt helps explain the odd orientations of certain ethnos, as well as other distant objects whose orbits appear almost perpendicular to the rest of the solar system. It's as if Planet 9 is dancing to its own rhythm, far above or below the cosmic plane, like a shadow weaving through the edges of the known. Interestingly, these simulations don't just explain what we see. They predict new phenomena. They suggest there should be more objects with highly inclined orbits, ones we haven't yet discovered. If astronomers find more such bodies in the future, it would strengthen the case for Planet 9. But mapping such a planet is anything but easy. Because of its vast distance, Planet 9 would move very slowly across the sky, perhaps only a fraction of an arcsecond per day. That's less than the width of a human hair seen from across a football field. Detecting such slow motion against a dense field of background stars is a daunting task. And then there's the issue of brightness. Planet 9 might be 5 to 10 times the mass of Earth, but that doesn't mean it's bright. If it's a gas giant like Neptune, it would reflect little sunlight at such a distance. It would appear as a faint cold dot, blending in with the darkness, possibly mistaken for a background star. Astronomers have to sift through enormous amounts of data from sky surveys, comparing images taken weeks or months apart, looking for that tiny, deliberate drift that might signal a distant planet on the move. Some sky regions, particularly those near the galactic plane, are filled with billions of stars, making this process even more difficult. It's like trying to find a single snowflake in a blizzard, using only a snapshot of the storm. Still, The search continues. Ground-based telescopes like Subaru in Hawaii have been scanning the sky. Space-based missions like WISE have contributed archival data. And new observatories, such as the Vera C. Rubin Observatory in Chile, are expected to dramatically improve our chances with their wide-field, ultra-sensitive imaging capabilities. Each passing year brings more refinement, better models, smarter algorithms, deeper images, and perhaps the moment when Planet 9 will reveal itself. But what if it doesn't? What if the models are wrong? Could the unusual orbits of ETNOs be explained by something else, like a collective gravitational effect, or even a previously misunderstood aspect of solar system dynamics? That's what makes this such a compelling mystery. We're not just chasing a planet, we're chasing the truth. And in doing so, we're learning how little we truly know about the outermost reaches of our own solar system. In the end, Planet 9 may be real, or it may turn out to be the greatest astronomical red herring of our generation. Either way, the journey to find it is rewriting what we thought we knew about gravity, planets, and the architecture of the Sun's domain. Imagine a silent, invisible force sculpting the edges of the solar system, gently nudging icy worlds, aligning their orbits and weaving structure into the farthest reaches of space. That's what Planet 9 may be doing right now. If it exists, Planet 9 acts as a gravitational shepherd. Its gravity subtly controls the orbits of distant ETNOs, not by brute force, but by persistent influence over millions of years. These objects aren't randomly placed. Their continued existence in those strange clustered orbits depends on Planet 9's gravitational presence. Here's how it works. When an object's orbit aligns just right with Planet 9's, it can remain stable indefinitely. The two dance around the Sun in a kind of cosmic choreography. But if an object strays too far, if its orbit drifts out of sync, the gravitational pull becomes disruptive. The object might be flung out, destabilized, or eventually pulled back into alignment. Over time, only those orbits that play nicely with Planet 9's gravitational field survive. This creates the appearance of order in what should be chaos. Even more fascinating, Planet 9's shepherding doesn't just organize orbits, it lifts them. Some objects are observed orbiting at extremely high inclinations, almost perpendicular to the rest of the planets. These steep angles were once a mystery, but now we know they may be the result of Planet 9 slowly and methodically sculpting those paths, like a river carving out a canyon. At first, the path is uncertain, unpredictable, but over time, the gravitational influence clears a track and structure emerges from the void. This isn't a conscious process. Planet 9 doesn't decide anything. It simply exists, a massive, silent object pulling on the fabric of the outer solar system. Yet, its influence is as deliberate and consistent as any sculptor's chisel. The analogy holds for a reason. Nature doesn't need intent to create beauty. In the vacuum of space, where there's no friction, no air resistance, even the smallest force, if applied consistently, can reshape the cosmos. And in this case, the force is gravity. This shepherding effect explains why distant bodies, despite their isolation, often follow remarkably similar orbital paths. It also provides an elegant answer to one of the most baffling puzzles in astronomy: why certain objects, like Sedna, appear to exist in orbits that simply shouldn't be there. Orbits too far away to be shaped by Neptune, too structured to be random. Planet 9 offers a solution. Its mass, distance, and orbital tilt combine to create a zone of influence, one that extends hundreds of AU across, powerful enough to sculpt the movements of icy objects that have never come close to the known planets. This process is called secular resonance, a slow, compounding gravitational influence that, over time, aligns orbital elements without direct interaction. Think of it as a whisper echoing through space, repeated endlessly until everything falls into rhythm. Without Planet 9, we'd have to accept that dozens of distant objects coincidentally adopted similar, stable orbits. That they just happened to cluster, just happened to align. But with Planet 9, the mystery becomes a mechanism, a cause, a purpose. And for scientists, that's not just exciting, it's empowering. It turns passive observation into an active quest. A search not just for a planet, but for the gravitational architecture that binds our solar system together. Still, questions remain. Could something else be responsible? Maybe a collection of small bodies working together to mimic a larger planet's influence? Could we be misreading the data due to observational bias, only seeing what we expect to see? These are valid concerns. Science demands skepticism. But even so, Planet 9 remains the simplest explanation that fits the known data. It unites scattered observations into a coherent story. And it pushes us to expand our vision of what the solar system really is. Not a neatly ordered family of 8 planets, but a wild, dynamic system with hidden members still waiting to be found. We often think of the solar system as finished, complete. But the truth is far more thrilling. It's still unfolding, still hiding secrets, and still being shaped, perhaps even now, by a world we've never seen. What if Planet 9 isn't just shaping the outer edges of the solar system, but tilting the whole thing? Astronomers have long puzzled over a strange anomaly. The Sun itself spins on an axis that's tilted about 6 degrees compared to the orbital plane of the planets. In simpler terms, the solar system, the swirling disk of planets, moons, and asteroids, leans slightly askew from the Sun's rotation. That shouldn't happen. If everything formed from the same rotating cloud of gas and dust, the Sun and its planets should align. So what could cause this subtle, persistent tilt? Enter the tilted solar system hypothesis, and with it, Planet 9. This theory suggests that Planet 9, with its massive body and inclined orbit, might be exerting a long-term torque, a twisting gravitational force, on the entire planetary system. To understand it, imagine the solar system as a spinning plate on a table. The planets are tiny weights orbiting in a flat ring near the center. Now, picture a heavy object, Planet 9, moving around the outer edge, but not flat like the others. Instead, it loops above and below the plate in a tilted wide arc. Its gravity tugs gently, persistently, pulling the spinning plate just off balance. Over billions of years, that tiny force adds up. Not enough to flip the plate, but enough to tilt it ever so slightly. That's what Planet 9 might be doing right now. According to simulations, if Planet 9 orbits the Sun at an angle of 15 to 25 degrees compared to the average planetary plane, its gravitational influence would gradually affect not just ETNOs, but also the orbits of the inner planets, Jupiter, Saturn, Uranus, and even Earth. The result? A system-wide tilt that subtly shifts the orientation of every planet's orbit. One slow, imperceptible nudge at a time. It's cosmic sleight of hand on the grandest scale. This idea was first proposed in 2016 by researchers who noticed that the observed tilt of the solar system could be explained by the presence of a massive inclined planet lurking beyond Neptune. The numbers matched. The physics made sense. And once again, Planet 9 emerged as the most elegant solution. Think about the implications. We're talking about a planet that not only reshapes distant orbits, but also bends the entire plane of the solar system. It's as if this hidden world is holding the celestial puppet strings, pulling on the architecture of our cosmic neighborhood. And we've never seen it. Some call this speculative. Others call it profound. But either way, it highlights a truth often forgotten in science. Unseen forces shape the universe just as powerfully as visible ones. If this theory proves true, Planet 9's impact is more far-reaching than anyone imagined. It's not just a rogue world at the edge of space. It's a dominant architect, subtly redefining the very shape of the solar system we call home. But there's still much we don't know. How massive is Planet 9, really? Where exactly is it in its orbit? And how do we distinguish between its gravitational influence and other possible explanations, such as the accumulated effects of multiple smaller bodies or early solar system instabilities? These questions are fueling a new generation of astronomical models and simulations. Advanced supercomputers now test thousands of hypothetical solar systems, altering variables, running forward and backward in time, searching for the fingerprint of a massive tilted world. And though we haven't directly seen Planet 9 yet, its influence may already be etched into the very orientation of the planets. As we probe deeper, one thing becomes clear. The solar system isn't as neatly ordered as our textbooks once suggested. It's a dynamic, evolving system, full of interactions, migrations, and hidden histories. And somewhere out there, Planet 9 may still be pulling the strings. As evidence builds for Planet 9, some astronomers are asking a bold question. What if there's no Planet 9? What if, instead of a single massive planet lurking in the dark, there's a swarm of smaller objects, icy bodies, perhaps hundreds of them, scattered across the outer solar system, whose combined gravitational pull mimics the effects of a single world? This theory is known as the distributed mass hypothesis, and it's gaining attention. It suggests that the unusual clustering of orbits among ETNOs could be the result of many smaller forces acting together rather than one dominant planet. Like a group of rowers, each tugging slightly on a boat, their collective pull could slowly steer the ship, even if no single rower is strong enough to do so alone. It's a compelling idea, but like all scientific theories, it needs strong evidence. Right now, that evidence is missing. We've detected only a small handful of ETNOs, and their distribution suggests a more centralized influence, something massive, steady, and consistent. But that could change. Enter the next generation of sky surveys. Projects like the Vera C. Rubin Observatory are poised to scan vast areas of the night sky with unprecedented depth and clarity. These surveys may reveal new distant objects, mapping their orbits and refining our understanding of what lies beyond Neptune. If astronomers discover dozens or even hundreds of mid-sized icy bodies spread across the outer reaches of the solar system in patterns that align with observed gravitational anomalies, the distributed mass idea could gain serious momentum. But if those objects fail to appear, or their arrangement doesn't support the necessary gravitational influence, the theory will weaken. Still, some researchers propose a hybrid solution. Maybe Planet 9 does exist, exerting the primary gravitational influence that shapes the ETNOs. But perhaps it isn't working alone. Perhaps there's a background population of other distant bodies, minor players contributing subtle gravitational nudges that add up over time. In this picture, the distant solar system is shaped not by a single architect, but by a hierarchy of gravitational forces, one dominant entity and many lesser ones. It's a layered structure, one that would mirror how gravity works throughout the cosmos. This wouldn't be unprecedented. Even in the inner solar system, small gravitational effects can have large consequences. For example, the Yarkovsky effect, a tiny force caused by sunlight warming an asteroid's surface, can gradually shift its orbit over decades or centuries. So while Planet 9 might be the main character in this cosmic drama, the ensemble cast of smaller objects could still be shaping the stage. But what makes Planet 9 such a strong contender is its ability to explain multiple phenomena at once. It not only accounts for the orbital clustering of ETNOs, but also explains the high-inclination objects, the strange orientation of the solar system, and possibly even the missing mass needed to model outer solar system dynamics accurately. No other single hypothesis ties together so many loose ends. Yet the scientific process demands caution. Astronomers are developing increasingly detailed simulations to test all theories: Planet 9, distributed mass, hybrid models, and more. They're comparing predictions against real-world data, checking for consistency, and searching for anomalies. And that's the beauty of this mystery. Every possibility leads to discovery. If we find Planet 9, we'll have redefined the map of our solar system. If we don't, we'll uncover an even stranger reality, one where many small bodies, collectively, bend the gravitational structure of our cosmic frontier. Either outcome reshapes our understanding of planetary science. As telescopes become sharper and algorithms more precise, the truth will come into focus. But for now, we're left with possibilities, each one exciting, each one pushing the boundaries of what we know. In the shadows of our solar system, something is shaping the orbits of icy wanderers. Whether it's one massive planet or a crowd of smaller ghosts remains to be seen. What if everything we thought we knew about gravity is incomplete? As astronomers continue to search for Planet 9, some scientists are looking in a different direction. Not outward into space, but inward into the laws of physics themselves. The reasoning is bold. Maybe the orbits of distant objects don't point to a hidden planet. Maybe instead they point to a flaw in our understanding of gravity. Let's step back. According to Newton's laws, stars in the outer regions of galaxies should move more slowly than those closer to the center, because there's less mass pulling on them. But that's not what we see. These stars move too fast, as if there's invisible mass pushing them along. To explain this, scientists propose the idea of dark matter, a mysterious substance that doesn't emit light, but exerts gravitational force. Billions of dollars have gone into detecting it. So far, no direct evidence. But there's another idea, one far more radical. It's called MOND, modified Newtonian dynamics. Instead of adding invisible mass, MOND changes the laws of gravity. It proposes that when gravitational forces become extremely weak, like at the edges of galaxies, gravity behaves differently. It becomes stronger than Newton's laws predict, eliminating the need for dark matter entirely. Most MOND research focuses on galaxies and the large-scale structure of the universe. But what if those effects also influence our solar system, particularly its outermost regions, where gravity is weakest? Some researchers suggest that the behavior of ETNOs, the strange orbits beyond Neptune, might not be due to Planet 9 at all. Instead, they could be the result of a modified version of gravity acting at extreme distances. Think about it. If gravity subtly changes in the outer solar system, then our models, based entirely on traditional Newtonian physics, could be giving us the illusion of a planet that isn't really there. This is more than just speculation. Recent simulations using modified gravity models have shown that they can mimic the same orbital clustering seen in ETNOs, without needing Planet 9. These simulations also predict that other planetary anomalies could arise from the same altered gravitational effects. It's a wild idea, but one that's gaining traction. Still, there are challenges. MOND theories must match everything we observe, not just the behavior of distant objects, but also the precision movements of known planets, spacecraft trajectories, and gravitational interactions across the solar system. So far, no modified gravity theory has done that perfectly. That's why many astronomers still prefer the Planet 9 explanation. It's grounded in well-understood physics. It fits with our current models, and most importantly, it makes testable predictions. If Planet 9 exists, we should be able to see it. But the allure of a deeper truth, one that rewrites the rules of gravity itself, is hard to resist. What if we're standing on the brink of a revolution, not just in planetary science, but in fundamental physics? History reminds us, from Newton to Einstein, every era of discovery has challenged the assumptions of the last. What if Planet 9 is our next moment of transformation? not because of what it is, but because of what it reveals. Whether the answer lies in a hidden planet, a swarm of icy bodies, or a new law of nature, the search is opening doors to ideas once thought impossible. And that's what makes science extraordinary. We look up at the night sky, expecting confirmation. But sometimes the universe answers with a challenge. What if you're wrong? As the search for Planet 9 deepens, a radical theory is emerging, one that blurs the lines between planetary science and cosmology. What if Planet 9 isn't a planet at all? What if it's a primordial black hole? This idea, once relegated to the fringes of theoretical physics, is now gaining serious consideration in scientific circles. The reasoning? It could solve two of the universe's biggest mysteries at once: the unexplained orbits in the outer solar system and the nature of dark matter. Primordial black holes are hypothetical relics from the early universe, tiny but incredibly dense regions formed moments after the Big Bang. Unlike stellar black holes, which form from collapsing stars, these ancient objects could be as small as an asteroid, yet as massive as a planet. Some theories suggest that these black holes might actually make up a portion of dark matter, the mysterious invisible substance believed to make up about 27% of the universe. And since dark matter tends to cluster around galaxies, it's not entirely impossible that one of these elusive objects could be hiding in our own solar system. It would be an incredibly rare occurrence, but rarity doesn't mean impossibility. If even a single primordial black hole resides beyond Neptune, it could help explain the gravitational anomalies observed in the orbits of Etnos. More than that, it could provide the first observable evidence of dark matter, offering a glimpse into the fundamental makeup of the cosmos. It would be a discovery that transcends planetary science, reaching into the heart of astrophysics and reshaping our understanding of the universe's origin. But how could we tell the difference? That's where things get tricky. Because a primordial black hole would be so small and dense, it wouldn't emit any light. It would be completely invisible, detectable only through indirect signs like gravitational lensing, where light from background stars bends slightly as it passes by the black hole. Some sky surveys are now looking for these subtle distortions. Others are searching for microlensing events, tiny, temporary brightenings of stars as a black hole moves in front of them. These methods are delicate, requiring immense precision and time. But even these techniques wouldn't necessarily confirm that the object is a black hole. A distant, massive planet could cause similar effects, disturbing orbits, bending light, warping gravity. Without a direct observation, distinguishing between a planet and a black hole becomes a matter of interpretation. Still, the black hole theory is being taken seriously enough that scientists are designing specialized missions to investigate. One concept involves launching small spacecraft with highly sensitive instruments to detect gravitational fields in the far reaches of the solar system. Another proposes using next-generation space telescopes to watch for microlensing patterns over years of data. The idea is bold, audacious, even a little terrifying, but that's what makes it exciting. Because if Planet 9 is a primordial black hole, it wouldn't just be the 9th planet, it would be the first black hole ever discovered in our solar system, and the first non-stellar black hole ever found. And that would change everything. It would reshape how we search the cosmos, how we define planets, how we think about dark matter, and how we understand the early moments of the universe, when black holes might have formed from density fluctuations smaller than atoms. Of course, this theory is still speculative. The evidence remains indirect, and the object, whatever it is, remains hidden. But the very fact that this idea is being explored shows just how mysterious our own cosmic backyard truly is. Planet 9 may not be a planet. It may be something far more ancient, far more exotic, and far more profound. If Planet 9 really exists, why haven't we found it yet? The answer lies in a perfect storm of cosmic challenges. Challenges so subtle and stubborn that they've kept this potential giant hidden from our view for decades. First, there's the issue of brightness. Planet 9, if it exists, is believed to orbit at an average distance of 600 to 1,000 astronomical units, AU, from the Sun. That's 600 to 1,000 times farther than Earth. At such an extreme distance, even a massive planet, 5 to 10 times the mass of Earth, would receive almost no sunlight. And what little light it does receive, it would reflect only faintly. Depending on its surface and atmosphere, Planet 9 could be hundreds to thousands of times dimmer than Pluto. To even detect it, astronomers would need long-exposure images taken under optimal conditions with highly sensitive instruments. But brightness is only half the problem. The other issue? Movement, or rather, the lack of it. Because Planet 9 is so distant, it would take approximately 15,000 to 20,000 years to complete a single orbit around the Sun. That means its motion across the sky is incredibly slow, barely perceptible over days or even weeks. Why does that matter? Because the most common method astronomers use to detect new solar system objects is motion tracking. Telescopes take repeated images of the same region, hours or days apart. Anything that shifts position between frames, a small moving dot against the background stars, is flagged for analysis. That's how Pluto was discovered in 1930. Clyde Tombaugh spotted a tiny speck slowly shifting its place over the course of several nights. But Planet 9 wouldn't move like that. Not even close. To our telescopes, Planet 9 would appear nearly stationary, just another faint dot among the stars. Unless astronomers return to that same patch of sky again and again over months or even years, they might never notice its subtle drift. And here's the problem. Most telescope surveys aren't designed for that kind of persistence. Observatories operate on strict schedules, often with competing priorities. Time on the world's most powerful telescopes is precious. Astronomers have to apply for observing slots, and only a small fraction of projects get approved. That makes it hard to dedicate months of telescope time just to watch one spot. Even worse, we don't know exactly where to look. Planet 9 could be anywhere along a vast orbital path covering a huge swath of sky. Searching it all would be like scanning a desert for a grain of sand. Only the sand is moving so slowly it's nearly invisible. And then there's interference. Some parts of the sky, like the galactic plane, are filled with countless stars, gas clouds, and background noise. A faint, slow-moving object could easily get lost in that clutter, even if it's right in front of us. All these factors combine to make Planet 9 a master of cosmic hide-and-seek. But astronomers aren't giving up. New approaches are being developed, some involving AI-powered algorithms trained to detect ultra-slow motion. Others rely on comparing archival images taken years apart to identify tiny shifts. And future telescopes, like the Vera C. Rubin Observatory, are being built with wide-field, high-resolution surveys in mind. Even amateur astronomers are joining the hunt, combing through public data from space telescopes like WISE and Pan-STARRS, hoping to be the first to glimpse the elusive planet. It's a global effort, fueled by curiosity, data, and the drive to uncover one of the greatest cosmic secrets of our time. And the truth is, we may already have photographed Planet 9. We just haven't recognized it yet. Somewhere in a digital archive, in a quiet data center on Earth, a few pixels may already hold the proof we've been chasing for decades. All we need is the right eye to see it. We've searched, scanned, and simulated. And yet, Planet 9 remains missing. Not because it isn't real, but because it might be hiding in a cosmic blind spot. Astronomers have narrowed down the possible characteristics of Planet 9 through process of elimination. If it were too massive or too warm, we'd have seen it by now. If it were too close, it would have appeared in previous surveys. What's left is a narrow but tantalizing range of possibilities. Planet 9 may be a mid-sized world, colder than Neptune, orbiting somewhere between 400 and 1,000 AU from the Sun. At that distance, it would be invisible to most optical telescopes and just below the sensitivity limits of even our most advanced infrared surveys. This is the astronomical twilight zone, a region that lies at the edge of our technological reach, a place where our eyes begin to fail and the shadows grow thick. In this zone, Planet 9 could drift silently for decades, evading detection not because it's cloaked in magic, but because it's perfectly positioned between what we can detect and what we can't. It's a frustrating reality for scientists. Every time a new sky survey comes online or a telescope pushes its technical capabilities, hopes rise. Maybe this time we'll spot it. But so far, Planet 9 has remained just out of reach, a ghost in the data. The real irony? We might already be looking straight at it. But because of its dimness and slow motion, it's hiding in plain sight, blending into the stellar background. And there's one more problem. We may be looking in the wrong part of the sky. Most surveys focus on the northern celestial hemisphere, where observatories in North America, Europe, and Hawaii are located. But Planet 9 might lie in the southern sky, a vast expanse that's been less thoroughly covered. This southern blind spot is massive. Covering it all takes enormous time and resources, especially since Planet 9 could appear as just a faint, unmoving dot among billions of stars. Even if you know what to look for, it's like trying to find a frozen firefly in a blizzard. But things are changing. With the construction of next-generation telescopes in Chile and the Southern Hemisphere, astronomers will soon gain unprecedented access to this unexplored domain. Instruments like the Vera C. Rubin Observatory will be able to conduct wide-field surveys of the southern sky at high resolution, night after night. It could be the breakthrough we've been waiting for. But even with better tools, the search won't be easy. Because Planet 9 exists in a middle ground, too faint for current optical surveys, too cold for infrared detection, and too slow-moving to stand out. It continues to evade confirmation. It sits in a liminal space, a gap between certainty and doubt, science and mystery. For some scientists, that's exhilarating. For others, it's maddening. And yet, there's hope in every new image, every scan, every pixel of distant sky that gets added to the archive. Somewhere out there, Planet 9 may be quietly orbiting, unaware of the frenzy it has caused. Unseen, but not forgotten. If Planet 9 refuses to shine, maybe we can catch it in the act of casting a shadow. While most detection methods rely on capturing light from a distant object, there's another approach, one so precise, so elegant, that it can reveal worlds hidden even from the most powerful telescopes. It's called stellar occultation. The concept is beautifully simple. When a celestial object passes in front of a background star, it momentarily blocks its light, causing a brief dip in brightness. Even if the object itself is invisible, too faint, too cold, too distant, its shadow still tells a story. For decades, astronomers have used this technique to study asteroids, moons, and Kuiper Belt objects. From these fleeting eclipses, they've measured sizes, shapes, and even detected thin atmospheres around icy bodies billions of kilometers away. But using this method to detect Planet 9 would be a different kind of challenge. First, the timing must be perfect. The occultation might last only a few seconds, and the alignment has to be nearly exact. You need to know the precise position of background stars, a reliable estimate of Planet 9's potential orbit, the expected path of the object relative to Earth, if and only if that orbit intersects with the line of sight to a background star, and we're watching at just the right time, we may catch that brief blink, a tiny star that vanishes for a heartbeat and returns. But here's what makes stellar occultation so powerful. It doesn't depend on the object emitting or reflecting light. It only depends on the fact that it's there, physically blocking photons from reaching us. It's one of the only tools in astronomy where darkness reveals truth. Planning for these events requires months of calculations, international coordination, and sometimes even airborne or remote observatories stationed in the predicted shadow path. Scientists have flown high-altitude planes into the occultation zone just to capture a few seconds of data. Imagine doing that for a planet we've never even seen. But if Planet 9 exists and its orbit can be narrowed down enough, stellar occultation might be the key to confirming it. Even a partial detection, a star dimming briefly and returning, could be the first concrete evidence that the object is real. And if we measure the duration of the occultation, we can estimate Planet 9's size, speed, and even density. If multiple events are observed, it's not just detection, it's a blueprint. Yet for all its promise, this method is also fragile. One cloudy night, one telescope malfunction, one bad prediction, and the opportunity vanishes. The next chance could be years away. That's why preparation matters, and that's why collaborations between professional and amateur astronomers around the world are vital. Some of the most successful occultation observations have involved small, ground-based telescopes operated by citizen scientists. In fact, you don't need Hubble to catch a shadow. All you need is timing, patience, and precision. And maybe, just maybe, the next time a star blinks for a second longer than expected, it won't be random. It'll be Planet 9, casting its silhouette across the stars, whispering, "I'm here." What if we didn't just discover Planet 9? What if we actually went there? The idea sounds like science fiction, but it's already being discussed by space agencies and mission planners. The challenge is monumental. The destination is farther than anything humanity has ever visited. But the reward, unprecedented. A robotic spacecraft sent to Planet 9 could unlock cosmic secrets about the formation of our solar system, planetary dynamics, and possibly even dark matter. But first, we have to find it. By the time such a mission is launched, likely decades from now, we'll hopefully have a much better estimate of Planet 9's location. But even tiny uncertainties in orbital calculations can compound over time, especially when targeting an object hundreds of billions of kilometers away. To succeed, the spacecraft would need adaptive navigation. That means onboard cameras capable of detecting faint celestial objects, a propulsion system that allows for mid-course corrections, possibly AI-based trajectory planning to react in real time to slight deviations. And then comes the issue of power. At distances beyond 10 AU, solar energy becomes practically useless. Even massive solar panels wouldn't generate enough electricity to power basic instruments. So like Voyager, Cassini, and New Horizons before it, this mission would require RTGs, radioisotope thermoelectric generators. These power sources rely on the heat from decaying radioactive materials, converted into electricity. RTGs are rugged and long-lasting, operating for decades with minimal maintenance. But they produce very limited power, just enough to run essential systems and scientific instruments. This limitation means the probe must be ultra-efficient, with streamlined instruments, onboard autonomy, and robust thermal protection. And because of the extreme distance, communication delays would be enormous. A one-way signal could take dozens of hours, so the spacecraft must be smart enough to operate independently, adjusting course, avoiding hazards, and recording valuable data even when Earth is out of reach. What would this journey look like? It would be long, a decades-long cruise, possibly using a gravity assist from Jupiter or Saturn to gain speed. Depending on Planet 9's exact orbit, the trip could take 30 to 50 years, meaning the team who launches the mission might never see its arrival. But imagine the moment the probe finally approaches, a dark world slowly materializing in the starlight. Instruments flicking on. Spectrometers, magnetometers, thermal imagers, all focused on this ancient frozen giant. We could learn its mass and density, whether it has moons or rings, what its atmosphere is made of, if it emits internal heat, and whether it holds secrets tied to the formation of the solar system. If Planet 9 turns out to be a captured rogue planet, a super-Earth, or even something entirely new, this mission would offer data that no telescope ever could. And perhaps most importantly, it would push the boundaries of what's possible. Just as Voyager 1 showed us the edge of the heliosphere, just as New Horizons revealed Pluto's icy heart, a Planet 9 mission would become a flagship of exploration for the 21st century. It wouldn't just expand our map of the solar system, it would rewrite it. Of course, the obstacles are many. The costs would be high. The mission would span generations. But isn't that what makes it so compelling? To chase the unknown, to reach into the darkness, and to touch something no human has ever seen. What if the key to reaching Planet 9 isn't bigger rockets, but light itself? While traditional propulsion systems rely on burning fuel, a new frontier is emerging in space exploration. One that uses photons, the very particles of light, to push spacecraft across the cosmos. It's called the light sail, and it could revolutionize the way we reach the outer solar system. Here's how it works. Photons don't have mass, but they carry momentum. When a concentrated stream of light, such as from a high-powered laser array, strikes a large, ultra-thin sail, it transfers momentum to the sail, creating a gentle but constant push. At first, the acceleration is almost imperceptible, but in the vacuum of space, with no friction and no fuel constraints, that push adds up. Over time, the sail picks up tremendous speed, propelled by nothing more than light itself. This is the core concept behind Breakthrough Starshot, a real-world project that aims to send microprobes to the Alpha Centauri system, our nearest neighboring star, at up to 20% the speed of light. At that speed, a probe could reach Proxima Centauri in just 20 years. For Planet 9, which is still within our own solar system, we wouldn't need to go anywhere near that fast. But even using a fraction of that velocity, laser sail technology could bring the timelines for a Planet 9 mission down from decades to mere years. Think about what that means. Instead of waiting 40-50 years for a traditional spacecraft to reach Planet 9, we could send an advanced, lightweight probe using a directed energy system and reach the outskirts of the solar system in less than a decade. And the benefits go beyond speed. Because light sails don't require heavy fuel tanks or complex propulsion systems, they can be extremely small and lightweight, perfect for launching in swarms, allowing multiple probes to explore a region simultaneously. In theory, we could deploy one probe for atmospheric analysis, another for surface mapping, a third for magnetic field studies. All launched in a single package, splitting apart in transit, each guided by its own sail. There are challenges, of course. Keeping a light sail stable over vast distances requires precise laser targeting. The sails must be made from materials thinner than a human hair, yet resilient to cosmic radiation and micrometeorites. And then there's the issue of communication. At such great distances, how does a tiny, fast-moving probe send data back to Earth? Engineers are working on miniature, ultra-efficient laser comm systems, powered by onboard RTGs, or capacitors charged before launch. If these technologies converge, high-powered Earth-based lasers, space-grade materials, autonomous navigation, and AI-enhanced imaging, then the dream of a rapid Planet 9 flyby is within reach. Even more compelling, this mission could be the proving ground for future interstellar travel. If we can perfect the laser sail system on Planet 9, the same approach could one day send humans, or robotic explorers, to other stars. In chasing Planet 9, we'd be doing more than finding a distant planet. we'd be testing the future of spaceflight, pushing the edge of speed, precision, and what's possible in human exploration. Finding Planet 9 is one challenge. Surviving near it? That's a whole different battle. Out in the distant reaches of the solar system, hundreds of times farther than Earth, the environment is unlike anything we've encountered. It's not just cold, it's perpetually frozen, lightless, and bombarded by cosmic radiation. Any spacecraft attempting to explore Planet 9 must be engineered for extreme survival. Let's start with the magnetic environment. If Planet 9 is a gas giant, it may have a magnetic field similar to Uranus or Neptune. This could create radiation belts, where energetic particles spiral along magnetic lines, capable of damaging systems or instruments on a probe if unprotected. If, however, Planet 9 is more like a super-Earth, it might have no magnetic field at all, leaving spacecraft fully exposed to solar and cosmic radiation. Either way, shielding will be vital. Thick multi-layer insulation, hardened electronics, radiation-tolerant processors. Then there's gravity. At that distance, the sun's pull weakens, and Planet 9's gravity, depending on its size, may be too feeble to reliably hold a probe in orbit. That means slower orbital velocities, longer orbital periods, higher chances of orbital drift. Maintaining a stable orbit could require frequent micro-adjustments. But here's the catch. Power is limited. With solar energy practically useless in that dark zone, spacecraft must rely entirely on RTGs, radioisotope thermoelectric generators. And those generate only a trickle of electricity. Every maneuver must be calculated. Every instrument must sip power, not gulp. There's no room for waste. Thermal management is another nightmare. In deep space, temperatures can plunge to near absolute zero. Without active heating, onboard systems freeze. But too much insulation, and you risk overheating from internal electronics. Ironic, isn't it? Engineers must walk a tightrope, retain just enough heat to operate, while bleeding off excess so nothing fries. It's a balancing act that even the Voyager probes, legends of space endurance, barely managed. And let's not forget communication delays. At those distances, even a high-powered signal could take 20-30 hours round trip. There's no room for real-time control. The spacecraft must be autonomous, capable of decision-making, navigation, and troubleshooting on its own. We're talking about a robotic explorer with AI-level independence. Add in possible dust impacts, unpredictable solar wind patterns, and data bandwidth limits, and it becomes clear. Surviving near Planet 9 is an engineering gauntlet, but that's also what makes it thrilling. It's the ultimate test bed for autonomous spacecraft, for deep space power systems, for adaptive navigation, for radiation-hardened tech. Master these, and we don't just explore Planet 9. We unlock the rest of the solar system and maybe even pave the way for future interstellar travel. So while the cold and distance are daunting, the mission is far from impossible. After all, we're not just building a probe, we're building a survivor. Planet 9's existence isn't just a question of where, it's a question of how. How does a planet 5 to 10 times the mass of Earth form 500 to 1,000 AU from the Sun, far beyond the known realm of planetary birth? Conventional models of planetary formation suggest that protoplanetary disks, the swirling fields of gas and dust that give rise to planets, don't last long around young stars. Just a few million years, at most. That's not nearly enough time to form a massive world so far from the Sun. So either our understanding of disk structure is wrong. Something strange happened in the solar system's early history. Let's explore both. Theory 1. A massive, extended disk. What if the early solar system's disk was much more massive than we think? If it stretched far beyond Neptune, retaining significant amounts of solid material, it's conceivable that Planet 9 formed right where it is, slowly, over tens of millions of years, but that would challenge existing models. Scientists would need to revise how material clumps and spreads in a low-temperature, low-pressure environment, how solar wind and gravity shaped the outer disk, how long such a disk could survive before dissipating. It would suggest our solar system is more dynamic and more complex than current simulations predict. And if that's true here, what about other planetary systems? Theory 2. Planet 9 migrated outward. Another idea? Planet 9 formed closer in, within the regions where Neptune, Uranus, or Saturn originated, and was later flung outward. This could have happened through gravitational interactions during the early days of planetary movement. If Jupiter and Saturn migrated inward and then reversed, as some models suggest, their shifting gravity could have destabilized other bodies. Planet 9 may have been ejected into a wide elliptical orbit, captured in a gravitational tug-of-war between giants, or even bounced outward through multiple planetary flybys. But how did it avoid being ejected completely from the solar system? For that, some astronomers propose a gravitational braking mechanism. Perhaps interactions with the Sun's fading protoplanetary disk slowed Planet 9's escape, capturing it in a distant, elongated orbit. Still, this scenario requires a perfect balance of force. Too much momentum, and Planet 9 is gone forever. Too little, and it spirals back in. The odds are narrow, which leads to the most radical idea of all. Theory 3. Planet 9 is an outsider. What if Planet 9 didn't form here at all? What if it was born around another star, a rogue planet drifting through space until our young sun's gravity captured it? Such stellar encounters were more common in the early galaxy, when stars formed in dense clusters. If another solar system passed close enough, it's possible one of its planets was torn away and adopted by the Sun. Planet 9 could be an interstellar orphan, now quietly orbiting our star from afar. If true, it would be the first captured planet ever confirmed in our solar system. That has staggering implications, not just for planetary science, but for the dynamics of stellar nurseries, interstellar migration, and even the origin of exotic chemistry in our own planetary neighborhood. No matter which theory holds true, Planet 9's presence is a puzzle, and solving it means rewriting what we know about planet formation, disk evolution, early solar system dynamics, and possibly the limits of planetary migration. One thing's clear: Planet 9 doesn't just challenge our models, it dares us to evolve them.